Imagine a material so fine, it's invisible to the naked eye. Yet, it holds the power to revolutionize the way we store energy. It's not magic. It's science at its most elegant. These are nanostructured materials, tiny structures engineered at the atomic scale. They're the secret ingredient behind batteries that charge faster and last longer. At the nanoscale, things behave differently. Materials can store more energy, conduct electricity better, and even respond to light or heat in ways we're only beginning to understand. This is the world of nanostructured materials, where the tiniest structures hold the key to the next big leap in energy storage. And today, we're diving into the science behind these materials and how they're shaping the future of energy storage. So what exactly are we talking about? Nanostructured materials are materials engineered at the nanoscale, just a few nanometers in size. These materials are designed to have unique properties due to their incredibly small size. Because they're so small, their surface area is enormous, which makes them highly reactive and efficient at storing and transferring energy. This is why they're so promising for energy storage technologies. In energy storage, these materials are often used as electrodes in batteries or supercapacitors. Their nanostructure allows for faster ion transport and more charge storage capacity. Nanostructured materials can also be designed to have specific shapes or patterns, which further enhances their performance in energy storage applications. In the next section, we'll dive into how exactly these nanostructured materials are used in real-world energy storage devices, like batteries and supercapacitors. You might not think about it, but every time you charge your phone or power a smart home, you're relying on energy storage systems that are quietly revolutionizing our lives. These systems are the backbone of modern technology. Yet, they're built using materials that are pushing the boundaries of science and engineering. Nanostructured materials are making these systems more efficient, longer lasting, and safer, without you even noticing. Understanding how these materials work can help you make smarter choices about the technology you use every day. It's not just about the gadgets you use. It's about the invisible science that makes them work, and the future they're paving the way for. In the 1980s, scientists first began exploring nanostructured materials for energy storage, inspired by the potential of atomic scale engineering to revolutionize battery performance. This period saw the rise of lithium-ion batteries, where nanostructured electrodes offered higher surface area and better ion transport, laying the foundation for modern energy storage. By the early 2000s, researchers started experimenting with carbon nanotubes and graphene, pushing the limits of energy density and conductivity in battery systems. The 2010s brought rapid advancements in nanostructured materials like silicon nanowires and metal oxides, which significantly improved capacity and cycle life in energy storage devices. Today, nanostructured materials are at the forefront of energy storage innovation, with ongoing research into scalable synthesis methods and integration into next-generation batteries. Imagine tiny building blocks, so small you can't see them with your eyes, but they're super strong and can hold a lot of energy. These tiny structures are like tiny batteries, packed with energy, ready to power your gadgets and cars. These materials are super fast at charging, like a superhero with lightning speed. They're also really safe, because they don't overheat like regular batteries, so they're perfect for the future. To begin, we need a setup that connects the energy source to the nanostructured material. This involves a battery or supercapacitor cell, where the material is integrated as the electrode. The nanostructured material is designed to interact with ions from the electrolyte. This interaction is critical for energy storage, as it determines how much charge the material can hold. During charging, ions from the electrolyte flow into the material's structure, creating a charge imbalance that stores energy. This process is carefully controlled by the cell's voltage. The structure of the nanomaterial, like its porosity or surface area, determines how efficiently ions can move in and out. This directly affects the energy storage capacity and speed. Once the ions are embedded, the material holds the energy until it's needed. This setup is the foundation of how nanostructured materials enable efficient energy storage. Once the material is prepared, the next step is the charge-discharge process. During this, ions move in and out of the nanostructured material's pores, creating a flow of electric current. The nanostructure allows ions to travel quickly and efficiently, which reduces energy loss and increases the speed at which the material can store and release energy. This movement is facilitated by the high surface area and controlled pore size of the nanostructure, which enables more ions to be stored and released in a shorter time frame. As ions enter and exit, they interact with the material's surface and interior, triggering chemical reactions that store or release electrical energy. These reactions are carefully engineered to ensure stability, safety, and long-term performance, making nanostructured materials ideal for advanced energy storage systems. Now we reach the clever twist: how these nanomaterials are engineered to store energy more efficiently than traditional materials. This is where the structure isn't just small, but strategically designed. Researchers introduce tiny voids or pores in the material, which act as energy traps. These create sites where charge carriers can accumulate without leaking, boosting the material's capacity. This clever twist is made possible through advanced synthesis techniques, such as atomic layer deposition, which allows precise control over the material structure at the nanoscale. These engineered nanostructures not only increase storage capacity, but also improve the speed and stability of energy storage, making them ideal for next-generation batteries and supercapacitors. In essence, the clever twist lies in the design: how these materials are built to store energy with precision, speed, and scalability, paving the way for a more sustainable future. At the core of nanostructured materials lies the manipulation of matter at the atomic scale, where the arrangement of atoms defines the material's properties. This level of control allows us to engineer structures that are both incredibly strong and highly conductive. These materials often feature nanoscale pores, tunnels, or layers, which act as highways for ions to move through. The precise design of these pathways is what enables high energy density and fast charging speeds. One of the most promising structures is the nanoporous electrode, which mimics the architecture of natural materials like bone or sponge. This allows for both mechanical flexibility and superior ion transport. Another breakthrough is the use of two-dimensional materials like graphene, where a single layer of atoms can act as a conductor, insulator, or even a catalyst, depending on its configuration. These nanostructures are not just about the material itself, but also the interfaces between different parts of the system. The way these interfaces behave determines how efficiently energy is stored and released. Imagine a city powered by a massive battery, but instead of a single heavy block, it's a network of tiny interconnected cells, each working together in harmony to store and release energy efficiently. Each cell is like a tiny factory, producing, storing, and delivering energy on demand, just like how your phone or laptop uses a battery to keep you powered throughout the day. These nanostructured materials are like the city's power grid, optimized for speed, efficiency, and reliability. But at a scale so small, it's like watching the miniature world work in real time. It's a gloriously dumb analogy, but it gets the point across. Nanostructured materials are the future of energy storage, and they're built to power our world, one tiny cell at a time. Before you go, if you enjoyed this, please give it a like and subscribe so you don't miss the next one. And tell us in the comments what you'd like us to make next. We read every single one. Thank you so much for watching. Comment this emoji if you made it to the end.